So we're going to pick up talking next about correlation in regards to scatter plots. And correlation is the way that we measure the strength of the relationship between two quantitative variables. So just some different things involving correlation. Correlation is always a number that's between -1 and +1. So if you think of an association being negative, uh, two variables that have a strong negative association have a correlation value that's close to -1. Two variables that are that have a strong association that's positive has a value for R that is close to +1. If you have an R value that is 0 or something that's close to 0, it means that the association between those variables is not very strong. So R being greater than 0 always indicates a positive association, where if R is negative, that indicates a negative association. Just remember what we mean about positive and negative association. So a positive association is as one variable increases, so does the other. A negative association would be as one variable increases, the other variable decreases. So just some other things, okay? The value of R, if it's close to 0 or equals 0, that indicates a very weak linear relationship between the two variables. And the strength of the linear relationship increases as R moves away from 0 and towards -1 or +1. So keep in mind that if we're talking about these extreme values here, R being -1, R being +1, they only occur in what's called a perfect linear relationship, meaning when the points line up perfectly in a straight line, which when we're talking about scatter plots really does not occur. So here are some examples of some graphs, some scatter plots, and what the corresponding correlation value would be for each of these. So if you take a look at just this one here, and say just this one here, and we'll kind of fill in some of the stuff in the middle there at the end. So you can see in this first graph, you have points that don't really arrange themselves in any type of fashion, linear or otherwise. That has a correlation of 0. But then you have these points here, and you can see they arrange themselves in a pretty strong linear type of fashion, and that has a correlation value that's close to -1. So keep in mind that because the points are moving in a downwards direction as you read them from left to right, that makes the R value a negative value when you do that. So here are some other ones here. This has a correlation of -0.3, so you can see points are still kind of all over the place, but they're certainly sort of in a more linear type of pattern than what this is here. Here's a correlation of 0.5, so you can see points are still kind of scattered, but they are starting to look a little bit more linear. Same kind of thing here. Here's a correlation of -0.7. So you can see the points are moving in a downwards direction from left to right, becoming more linear than the previous graph. And here's a graph that has a correlation of 0.9. And you can see here the points are moving in an upwards direction as you read them from left to right, and that's what makes this R value a positive number there. So what I'm going to show you in your calculator is how you compute these values for R. And really what we're looking for when we're talking about correlation is we're trying to just use this R value to measure the strength of the relationship between two variables. So you can calculate R in two different ways. One is you can use your calculator, which is what we're going to use. But there is a way to do it without a calculator. I'm going to show you this formula here, and hopefully by the end of this you'll see why we use our calculator to do this. So the value of R can be computed by this formula here, and that is 1 over n minus 1, remember n is the number of data points, times the sum of, and you have to do this for each data value, you have to take the data value, you have to subtract it from the mean and divide it by the standard deviation of the x values, and then you take that answer and you multiply it to the y value of one of your points minus the mean of the y values divided by the standard deviation of y. So you would have to do this right here for every single point that you have in your scatter plot. So that would take a while to have to do that by hand, which is why we I strongly encourage you to use your calculator when you do this moving forward. So in terms of just some different things examples wise involving scatter plots. So I'm kind of referencing once again the scatter plot from the previous notes on the body weight versus pack weight for the 8 hikers scatter plot that we did. And from this data we determined that the value of R is positive 0.795. So part A asks to interpret the value of R in context. So what does an R value of 0.795 mean in the context of that particular problem? So because you have a value of 0.795, okay, what this confirms is there is a moderately strong positive linear relationship between body weight and pack weight for these 8 hikers. So that basically interprets the value in context. It's probably one of the harder things to do when we talk in statistics about interpreting values in context. Part B asks, what effect would removing the hiker with the heaviest body weight from the data have on the correlation? So if you recall from when we talked about this particular scatter plot in the previous notes, we had mentioned that the hiker that had the heaviest body weight had a pack weight that didn't really seem to fit the pattern of the other points, and we said that that particular data value could have represented an outlier. So one of the things that will happen if you remove that point is it would make the pattern seem to fit an even more tightly clustered linear pattern. So what that would do if we remove the outlier is it would increase the correlation. So some of the things that occur with correlation, and this is probably the most common mistake people make when they're talking about correlation, and that is, while a strong positive linear relationship has a correlation that's 1, or if it's negative, -1, a correlation near 1 doesn't mean that the relationship is linear. Your calculator will compute correlation for any type of scatter plot, linear or otherwise. And one of the things that you don't want to sort of fall victim to with this is just assuming that your scatter plot is linear and computing the correlation without actually looking at your scatter plot first. Because, and I'm giving you this example down here, if you were to create a table of values for this equation, y equals x squared, for instance, if you put some values in L1 for x and you put the corresponding y values in L2 and you computed the correlation for that, you would get an R value of 0.97. So you're going to get a correlation value that is very close to 1, even though you're talking about a relationship that's not linear. And the key thing here to remember about correlation is that correlation, for the purposes of what we're talking about with scatter plots, only applies to graphs that are linear. So one of the things to make sure that you do before you start to look at anything involving the DOFs of scatter plots or things like that is always make sure that you check the form first. I'll just sort of make a note of this at the bottom here. Always check your form first. Because if your scatter plot isn't linear, then all these things that we're talking about, in particular here, correlation, do not apply. Correlation only applies to graphs that are linear. But like I said, your calculator will compute correlation for anything, linear or otherwise. But for the purposes of what we're looking at here, the R value really only has significance for scatter plots that are linear. So here's just some checkpoint questions, and I'll give you a few minutes once you try to work these out on your own. So for these questions here, you have 4 graphs, one of which measures the number of boats that are registered in Florida versus the number of manatees that are killed by boats. This graph here is the number of storms that are predicted versus the number of storms that actually occur. This graph here is the healing rate for limb 1 versus the healing rate for limb 2. And then you have for here last year's percent return, using that to predict this year's percent return. So the first checkpoint question asks to interpret the value of R in context for each one of these here. So for part A, interpreting this in context, we would say there is a strong positive linear relationship between the number of boats registered in Florida and the number of manatees that were killed. So that's part A. For part B, we would say the correlation's about 0.5 approximately. So for that, we would say that there is a moderately positive linear relationship between the number of storms predicted and the actual number of named storms. For part C, correlation is, I don't know, maybe around 0.3. And because of that, we would say that there is a weak positive linear relationship between the healing rate of the two front limbs of the newts. And then for part D, correlation is roughly around negative 0.1. So we would say that there is a weak negative linear relationship between last year's percent return and this year's percent return in the stock market. So that was the first question. The second question, it says the scatter plot in B contains an outlier, the disastrous 2005 season, which had 27 named storms, including Hurricane Katrina. What effect would removing this point have on the correlation? So just remember that for something like this, the correlation would decrease. Okay, this point has the effect of strengthening the observed linear relationship we see. And that would be, let's see here, that would be this point right up here. So because that point has such a higher storms observed value versus the storms predicted, that would actually decrease the correlation rather than increase it. And that's the kind of point, and we're going to look at this in the next lesson. We would say that that particular point is what's known as influential. It's not necessarily an outlier, it's just more of what's known as an influential point, and we'll talk more about that next time. So just some facts about correlation. One would be this. Correlation makes no distinction between the explanatory and response variables. So make sure when you're creating a scatter plot that you put your explanatory variable on the x-axis and you put your response variable on the y-axis, because correlation does not differentiate between the two. In terms of some different things with transformation, the value of R does not change when we change the units of measure for both x and y or both. So remember that we talk about how shape never changes whenever you add, subtract, multiply, or divide a constant to your data values. Well, R has the same kind of effect. Okay, R does not change no matter what you do to your data. And the correlation value, R itself, has no unit of measure. So for instance, if we were doing a scatter plot and we were measuring our data in inches, we wouldn't say that the correlation value for something is 0.5 inches. We would just say the correlation value is 0.5. R has no unit of measurement. And just some other things to kind of be aware of with correlation. One is correlation only applies to scatter plots, which means you have to be talking about two variables that are quantitative. Big thing there. Correlation does not describe curved relationships. Correlation is only involved with relationships that are linear. So with this one right here, make sure you plot your data. Just make a note of that. Make sure you plot your data. Correlation is not resistant, and by not resistant we mean that it is strongly affected by observations that are outliers. And then finally, correlation is not a complete summary of the two variable data. So remember, correlation speaks to of your DOFs, direction, outliers, form, and strength. Correlation speaks to the strength. So correlation is a piece of the description, but it's not the entire description. So those are just some different basic things involving some things with scatter plots. One of the things that we're going to get into looking at as we kind of move forward is some things with scatter plots involving lines of best fit. I'm going to show you some more things with your calculators in terms of how to compute correlation, how to compute what's called the R squared value. We're going to get into looking what the value of R squared is, and how you can use your calculator and your line of best fit to take a scatter plot and make predictions.